Okay, now we're going to do the same problem to see if there's any differences between the four group means in the population by filling in these missing blanks in the Anova table and computing the F statistic through this table. Now, let me remind you that on the final, you're not going to be filling in tables because it's a Scantron final. So I think what I could do for you is provide you with tables because people have requested this so that you can fill them out on your own because they make it, you're used to doing that and it makes the structure clear, but just ask you for particular cells. So for example, one of the questions might be from this table, you know, what is R squared, for example? And you could say, okay, R squared, you should know, is the proportion, R squared is going to be the proportion of the variability, of the total variability due to the model, so it would be SSB over SST. So you could, or SS, we usually call it SS model over SST. And so in this case, it would be 126,601 over this. And that is 0.09. Okay. And now for, how are you going to, so filling out this, you can fill in the whole thing as usual, but I'm just going to be asking you just pieces of it on the final. All right, so why don't we fill in the whole thing together? So you know this plus this has to add up to that, so this one's easy. Now, how are you going to remember these degrees of freedom? Okay, now the total is always n minus 1, right? And you have to, and n is what? N was from the previous page, 894, and the number of parameters that we're estimating is, we're estimating 4 parameters. We're estimating one for each group, the mean of each group. So the number of parameters is 4, and it's always the same as the number of groups, same as G, number of groups. Okay, there are 4 different groups. So, so here, this is going to be P minus 1, and this is N minus P, and they all add up, right? Okay, see? So here we have, this is going to be 3 then, and this will be 890, and this is 893. All right, and then the F ratio here can be computed as, this is just given as just SSB over MSB, right? So it would just be, excuse me, SMS, the mean square model over the mean square within, right? That's what we want to do. Okay, and so that is this divided by that, and you get 29.34. And is, okay, so is P less than 5%? Well, you should just know right off the bat, that's a huge F, right? Yes, you don't even need a table to decide. Why? Because, why don't you need a table? Because remember, when the null is true, the mean of the F stat, the mean of the F statistic is what? Remember, is 1, approximately 1, very close to 1, and very close to 1. And the mean of the chi-square statistic is the number of degrees of freedom, is the degrees of freedom, which in this case would be 3. Okay, or the number of parameters minus 1, which is 3. Okay, so let's see what else we need to do here. So this is just going to be the square root of the mean square within. And I think that's pretty much it here. Okay, and as we said before on the previous page, this F ratio, this right here, we did this before, can also, we did it here back on page 225, then this is exactly the mean square model over the mean square error, or the mean square between over the mean square within for groups. That's the same thing. Is also, you can see it's also the same thing as that, computing it directly from the R squared. If you have the R squared, this is the easier way of doing it. Okay, so now let's look at our next problem. And here we are. Okay, so now we're on this exam 3 material. And the first question is about transformation of variables here. Okay, so it says, suppose you'd like to do a linear regression, but your scatter plot's not close to linear. You see the histogram of the y variable is right skewed, and you want to transform it to be more normal. Remember, if it's right skewed, that means it has that long right-hand tail, and we want to bring those values in. And so we want to do either, this would be our first step, and if that doesn't bring them in enough, then this is our next step. You tried one of the transformations, and it was a step in the right direction, but didn't go far enough. You tried another, and it worked very well, so you must have tried the square root, which is a less extreme transformation, and then the log. All right. So when can you use logistic regression? You can use logistic regression when what? You use logistic regression when the y variable, what you're trying to predict, can be coded as what? Ones and zeros. All right? When it can be coded as ones and zeros. So which one of these can be coded as ones and zeros? Predicting income, no. You can't say can't code that as ones and zero. That's a numerical variable. Predicting graduating with honors, yes. If you graduate with honors, it could be a 1, no, 0. So this is yes. This is no. Reaction time, no, that can't be. If the reaction time is above a certain level, that could be, but not just the reaction time. Predicting having a fatal car accident, yes or no? Yes. You can code that as ones and zeros. So this could be logistic regression. All right. Now for this, again, you're not going to be given that table. So in some ways that makes it harder because things aren't as step by step. So I would just maybe give you just one, say, okay, you know, if 1 minus p was 4/7, what is the log odds, let's say? So you would have to do what? You'd have to figure, okay, well, what's the odds? The odds are, first of all, you know these two have to add up to 1. So the odds is p over 1 minus p. So in this case, it would be 3 out of 4. So sometimes you're going to have to skip steps, but I might just provide you with the table and just ask you, because people requested that, and just ask you for certain cells so you can go ahead and fill it out, and then I'll just ask you for a few of these cells. I think that would be the probably the way to make it as close as possible to the practice exams. So then you would just take the log of that, and that's negative 0.29. All right, and so now you know when the log odds are 0, that means the odds are 1, right? You just exponentiate that, and this is 1-to-1 odds means what? Means that it's a 1/2 to 1/2 chance here. So when the odds are 4-to-3, what does that mean? That's success over failure. So you can think of it, okay, there's a total number of outcomes of 7, and there's 4 successes and 3 failures. Or if you didn't, so I guess that's the easiest way to do it. And then the odds of 4/3 is 0.29. These, all right, not the odds, the log odds, the log of 4/3. And notice those are symmetrical, 3, because they're reciprocals of each other. All right, now there's 3 forms to the logistic regression equation, and the probability form is always this S-shaped curve that's bounded at probability goes between 0. This is the y-axis is probability, 0 and 1. And this is the probability form, okay? And then the odds goes between 0 down here to positive infinity up here, goes up, you know, this is an exponential curve, and that's the odds form is A. And then the log odds form, which is a line that goes from negative infinity, it goes all the way down to positive infinity, and that is, the line is the log odds form, so that's C. So this is a line, this is that S curve, and this is an exponential curve. Okay, so let's go to our next question. And this is a question, let's look, see what it says. Okay, so on our survey data, we asked these 3 questions. Are you for banning the possession of handguns for private citizens? It's a 0, 1. And we're going to predict that based on how many hours per week you call your parents. That's a quantitative variable, and are you white or not? Okay, and so below is the output for the logistic regression model predicting the probability of being pro-gun control. And for answering yes to that question. From what? From, I guess this was cut off here, but it's from how many hours you call your parents and from whether you're white or not. There. And it says a chi-square test was done for the overall regression effect, the overall. If the sample was smaller, could you have done an F-test? Remember, no. The answer is because we never do, remember this, you never do F or t-tests in t-tests in logistic regression because the y variable is counts. And there you go, in logistic regression. All right. Now, so calculate the Z statistic. All right, so this is missing right here. This is missing, and we're supposed to calculate what that is. All right, well, it's just going to be, it's pretty obvious, it's just going to be the standard 0. This is the observed slope minus the expected slope of 0, right, over the standard error for the slope. So that's the answer. And what's your p-value? You're going to have to look at, first of all, it's a two-sided, so we'll draw a normal curve. And we just want to figure out what the middle area is there for 2.18. So if we look at 2.18, the directions say use the closest line on the table, so that, and you can round to the nearest whole number. So 97% in the middle for there. Okay, so we'll put 97 in the middle, 97%. And that means that the tails right here, because we're going to count both tails. Why? Because it's a inequality. There's no direction there, so we don't know whether it's going to go in this direction or that direction, and that is 3%. If we specified a direction, then that would be halved to 1.5%. Now, are whites more or less likely to be for gun control? Well, we have to look at the slope for white, and it's negative, so that means less likely. assuming the number of hours they talk to the parents are the same, because it's a multiple regression. So it's saying, oh, you compare two people who have the same communication with their parents, the same value there, and then this is how much difference being white makes is, and it's negative. The more phone time with parents, so look at that, that's positive, so that's going to make it the higher, the probability of being for gun control. Makes sense, okay, because this has a negative slope here. Now, what's the log odds equation? Okay, so those are just given to us right here. This is the intercept. There's the slope for white, and there's the slope for the number of hours talking with parents. And the odds ratio is just e to the slope. So it's going to be e to the slope for whites, which is -2 here, which is equal to what? 0.135. So this means that the odds of a white being for gun control is just 0.135 times the odds of a non-white being for gun control, assuming the same number of hours. So let's look down here at this table, and it says, all right, so let's say we're trying to figure out the log odds and the probability here. And again, let me remind you, you're not going to have tables like, okay, so 0, so you just stick a 0 in for hours, and the person's white, so they have a 1 here. So the log odds are just 0.76 minus 2 times 1, which is equal to -1.24. And then the odds are just going to be e to the -1.24, which is 0.29. And then the probability is equal to the odds over 1 plus the odds, right? And so that's 0.29 over 1.29, which is equal to 0.22, I think. Let me just check. It's equal to, yeah, 0.22. Okay, so I'm just curious, what would it be for non-white? They only have, let's just say they have 0.135 odds, but remember, that's not going to tell us how the probability changes. Here we actually have to do it because probability depends on the actual values here. So this is, okay, so this is going to be what? And non-white, what would you put in here for non-white? You would put in, we're back here at that equation up here. So for non-white, it's just 0.76 because there are zeros for the other two values, right? And so that's e to the 0.76, which is 2.14. So the probability is 2.14 over 3.14, which is equal to 0.68. So for comparing a white to a non-white who don't talk to their parents very much, the difference in the probability of them being for gun control is quite different. So non-whites are just much more pro-gun control than whites. That's 0.68, not percent, 0.68. Let me just write that more clearly. 0.68, which is 68%. Okay, now we're on the next one. And now we're finally at the nonparametrics. Okay, so this is the nonparametrics, question 15. And so what are we doing here? A randomized blind test was done to test the effectiveness of a drug to cure warts. The subjects were 8 people with lots of warts. 4 subjects took the drugs and 4 took the placebo. The number of warts that disappeared for each of the 8 subjects is recorded below. Okay, this is a good case of doing a nonparametric test because we don't know the distribution of the number of warts of these. We don't know either of these distributions, and it's there's clearly, we don't want to weight that outlier too much. So this is a good case to do non-parametric. So what do? We change all these numbers to ranks. All right, let's do that. So this is what we mean is we're just going to change them. There's 8 numbers here. We're going to change them to integers between 1 and 8. The lowest one will be 1, and the highest one will be 8. Right? 1. What's the next? Then 2. And this one is 3, 4, and 5. They're all in a row. Then this is 6, 7, and 8 if we rank them in order. All right, so now we're going to add them all up for the drug group here. So if we add those up and we add all these up, what do we get? So we get 22 here and 14 here. So that's 22, that's 14, and together they equal 36. We should check right away, is that right? Remember, the numbers between 1 and 8 are going to be equal to what? So check that that's equal to n times n plus 1 over 2. So check it's equal to 8 times 9 over 2, which it is. Okay, so that looks good. Now the expected rank sum for each one's going to be what? Well, it's the same as this formula right here. This is like the average right here of the numbers between 1 and n, and this is just how many observations you have. So for the rank, for the expected for each group, that n is just replaced with the how many, it's going to be n sub I for each group times n plus 1 over 2. So each of these groups has 4 members, so it's going to be 4 times what? 9 over 2. So this is 18, and this will be the same. Why are they the same? Because there's both the sample sizes in each group are the same. So that adds up to 36. 2. And now the observed minus the expected. This is a good check. Now you're not going to be filling out this whole table. So, I probably won't give you this whole table. I don't think you need this, but it's nice to see that 22 minus 18 is 4, and 14 minus 18. The difference here is negative 4, and the observed, they have to sum to 0. But, okay, so I probably, you're not going to get a question where you have to fill out a whole chart. I would just ask you probably what the rank sum is, maybe what the expected rank sum is. Now, the sample sizes are too small to use a normal approximation, but let's assume that you could for the purpose of this exam. And so we have the null is that the drug works no better than the placebo, and the alternative is it does work better than the placebo for some segments of the population. And so now we're going to compute the Z. So what is the Z? So the Z for the drug group. So it's the observed rank sum, which is 22, minus the expected, it's that 4 right there, over this standard error. So this will be given to you. So it's just, what is it? It's, those are the sample sizes for the two groups, 4 times 4, and n plus 1, that's 9 over 12. So this is the square root of 12. So that's what's going to go down here. And I got approximately 1.15 is the answer. So now let's assume that this was large enough to follow the normal distribution, and let's do the let's calculate the p-value. All right, so as a z-score, this is what we have, and as a rank sum, this is for the drug group, we'd expect 18, and instead we got 22. Where do we put 22 on here? Well, that's what this tells us. We put it right there. That's 1.15. That's where 22 lands. And so do we have one-sided or two-sided? That's a good question. We have to, how do we know whether we're going to, let's look up 1.15 first. And look up 1.5, and we get 11.92. Whoops, that's 0.15. Where's 1.15? That's 75%. All right. So we have 75% in the middle between negative 1.15 and 1.15. And we want to know whether to do one-sided or two-sided, so you just have, that depends on what? The alternative. And it specifies a direction. It says it's going to be here. The drug does better than expected, than the placebo. So it's higher rank sum. So it's just this. So it's one-sided because the alternative specifies the direction. So we have 12.5%. It's 12.5% there too, but this is the p-value. So what do you conclude? Well, do we reject the null? No, not at 5% certainly. I mean, that's a very high, it's very likely to have happened by chance. Not very likely, but 12.5% is too high a p-value. So we cannot reject the null. We would have had to, the chance that we would have seen this big a difference between 22 and 18 just by the luck of the draw is 12.5%, which isn't strong enough evidence to reject the null. So it's plausible. So it's, we're not accepting the null. We don't know for sure that they're the same, but we cannot reject it. It's plausible that it's no better. All right. So that's what we have there, and let's continue. So now, what's the U statistic? So now we're going to do the same thing by the U statistic, and of course it should give us the same answer, but the U statistic counts how many times each observation surpasses all the observations in the other group. So, let's look. So 0 loses to all of these. It's less than all of those, right? And 10 is better than all of them, 11 is better than all of them, and 40 beats all of them. So they each have a score of 4. They beat everybody on this team, right? And how about this one? This one, 5 beats 0, but so it just beats 1. 6 just beats 0, 7 just beats 0, and 9, 5, 6, and 8, and 9 just beat 0. Each one of them only beat 0. So each one of these has a rank, a U count of 1. Just beat 1. Surpasses one of those scores in the other group. So this adds up to 12, and this adds up to 4. Now, how are we going to check? Let's make sure we're right. The sum of two group U statistics must be what? Well, it's going to be for any two groups with 4 members each. Well, it's going to be how many possible comparisons are there, pairwise comparisons. There's the number for each one of those 4 people. There's 4 comparisons we're making, so it's 4 times 4. If there were 6 people here, for each one of these 4, you'd multiply, there'd be 6 comparisons. So it's, remember it's N1 times N2. So in this case, it's 16, and that adds to 16, so we did that right. All right, now, would you get the same Z stat and P stats using this, the U statistic, as you do? Yes, you would. Exactly the same, right? Okay. Now, you see you have these observed minus expected of 4 and negative 4. And here you're going to have an observed minus expected of -4. And what's the observed? The expected, excuse me. I didn't do that. This is the total, but what would the expected be? I didn't ask that, but let's see, what would the expected be? The expected would be, since there's 16 possible matches, and under the null, you'd expect half to be won by one team and half by the other. So the expected for each, here's what the U statistic, here's the observed. If I asked you what the expected was, it would just be 16 divided by 2. So it would be 8 and 8. And there's where those differences would be the same. All right. So for the U statistic, no matter how many people are in, how many observations are in each group, the expected is going to be the same for each. It's just going to be always the expected is expected. U is going to be N1 times N2 over 2. And it doesn't matter if those are the same. It's the same for each group. Now that's different than here, where the expected here, the way we got these, is will change. And for this, if one group has 3 and another group has 4, this expected will be different. They happen to be the same here only because there's 4 members in each group. Okay, let's see. Now, finally, what is this one? This is the test that's the parametric, non-parametric equivalent of Anova. So now we're comparing 3 groups. There are 3 forms of this final. Suppose at the grading meeting I randomly select 9 finals and grade them with these results, right? The null hypothesis is I want to see if there's a difference in difficulty between the 3 exams. The null is no, there's not, and the alternative is yes, at least one of the exams is of different difficulty in the whole population. So now what are we going to do? So we first have to change them to ranks. Oh, these are just in order. Look at this, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So the rank sum for Form A, you just add those up as 6. For Form B, you add those up as 15. And for Form C, you get 24. And what is the rank sum? Should I check? 6 plus 15 plus 24 should equal what? Well, it equals 45. What should it equal? It should equal, for any set of 9 numbers, you just add up all the 9 numbers, that's going to be what? That's going to be 9 times 10 over 2, which is equal to 45. So it checks. 6 plus 15 plus 24 is equal to 45. Good. Now we get this H-stat, and would any other arrangement of 9 numbers into 3 groups yield a higher H-stat? A higher H-stat, the higher the H-stat, the more difference there is between the groups. Is there any way to order these that would be more extreme? Look, there's no overlap. The 3 worst people in one group, the 3 best people in another. There's no way to make it a bigger difference between the 3 groups. So, no. That's the most extreme data we could get. Now, for large enough samples, we can best approximate the distribution of the H-stat with. We're comparing 3 groups, so it can't be a Z. It's never going to be a T or an F. It is a chi-squared. Okay. Finally, we're almost done. So now we're going to, there's just these 3 questions left, and these are on the non-parametric equivalent of the correlation coefficient, the Spearman rank correlation coefficient. And so if we decide to do a non-parametric test and use this Spearman correlation coefficient to test the null hypothesis that the population correlation is 0, then the appropriate test statistics for small samples, well, for small samples, for all these non-parametric tests, you look at the exact probability distribution. It's not hard to do because the numbers are uniformly distributed, so it's easy to calculate this. Then for large enough samples, the appropriate test statistic is what? We don't use the T or the F. It's the Z. All right. Now, look at the 3 data sets below. For which data set is R not equal to RS? Well, first let's get RS for each of these. We're going to compute R based on the actual numbers, and then we're going to compute RS when we change it to ranks. So here's the data set. Let's change them to ranks. So the first numbers are already in ranks. We do them separately. You do the X's first. Well, they're already in order, 1, 2, 3, 4. And now we're going to change the Y's to numbers between 1 and 4. And this is the smallest. This is the next smallest 4. So they're in order, ascending order as well. Now, this is R. For this one, RS is equal to 1. For this one is RS equal to 1. Yes, this is, if you plotted this, it would be a line. It would be this right here. So this data set 1 also has R equal to 1, because you can see that Y is equal to 2X. All right, let's do our next one. So now if we put this into ranks, what do we get? This is let's do the X's first, 1, 2, and 3. Smallest, whoops, that's the biggest. So that's right, if we put it into ranks, we have 3, 2, and our smallest is -3, 1. How about these? When we put these into ranks, again, this is our biggest and that's our smallest, so it's 1, 2, and 3, right? Is that correct? Yep. So this is the biggest. So here, this RS is equal to 1, and this is what? So does this also have R equals 1? And you might not see that at first, that R is equal to 1 here, because Y is equal to X plus 6. But let's say you didn't see that, and you wanted to, so you could just plot those 3 points, because it's just 3 points here. So let's do that. And so let's say we plotted them. So 1, 2, 3, 4, 5, and -1, -2, -3. So you have -1, 5, then you have -2, 4, and then you have -3, 3. And you can see they're all on a straight line there. Okay, so how about this last one? This last one in ranks is what? This is 1, 2, 3 for the X's, 1, 2, and 3 for the X's, and for the Y's, it's also 1, 2, and 3. So again, RS is equal to 1. But here you can see, obviously, these 3 points don't fall on a line. So for which data set is it not? It's data set 3 is the only one. Okay, so that's it for this exam, and that's all.